Hello, Union High School Pre-Calc. It's Mrs. Peterson again. Welcome back. We hope that you are doing well, that you're staying on top of your schoolwork, also hopefully finding creative ways to sort of serve and help those around you. We are in week 4 now, so we've got 2 more weeks of distance learning, so we're really wrapping it up here. This week we're going to be looking at sequences and series, so a lot of this should look familiar from Algebra 2. Today you're going to be looking at arithmetic sequences and series, and then you've got a My Math Lab homework over this, and then the next video will be on geometric sequences and series, and you will have My Math Lab homework over that, and then your final My Math Lab homework over sequences and series will just be kind of a recap of both lessons, and then we ask that you fill in the Google form check-in as well. A little bit different this week, all homework is going to be due on Friday at 9 as opposed to Sunday, trying to curve that procrastination a little bit. And do keep in mind that homework has to be at least a 75% on all My Math Lab assignments this week and next to be eligible to take that last assessment, which remember can help both your quiz and test categories. As always, if you've got questions, please reach out to your pre-calc teacher. All right, let's get started here. So this is actually the example I always start out with, whether we are experiencing coronavirus or not, and I thought that it was particularly applicable for today. So say that a virus contaminates an initial population of 1,000 people. The virus spreads and the number of people infected doubles each day. So we can write this data as the following sequences of numbers: 1,000, 2,000, 4,000, 8,000, 16,000, etc. So really we can think of sequences as functions that have a set of positive integers as their domain. So if you look at the red numbers there on the top, 1, 2, 3, 4, 5, etc. Domain is the set of positive integers, and the sequence can be either infinite or finite in length. So it can go on forever or it can stop at some point in time. Okay? So you don't need to write anything down yet, maybe just sort of pay attention to this definition and first example. Again, hopefully a lot of this looks familiar from Algebra 2. So a sequence is an ordered list of numbers. The first number or first term in the sequence is typically denoted as a sub 1. So in English, we would say the first term. In math, we would call that a sub 1, so like a subscript of 1. Okay, in English, we would say second term. In math, we would denote that as a sub 2. Okay, so those are equivalent. The nth term, then, is denoted by a sub n. Okay, so the 5th term, we would write it as a sub 5, the 100th term, a sub 100, so on and so forth. Okay, so example 1, find the first 4 terms, in other words, the first 4 numbers, and the 20th term of the sequence given by a sub n equals 5n minus 3. So the first term, remember we denote that as a sub 1, meaning anywhere I see an n, I'm now going to replace that with a 1. So very similar to a function, right? So 5 times 1 minus 3. The second term will be denoted as a sub 2, so 5 times 2 minus 3. The third term will be denoted as a with a subscript of 3, so 5 times 3. I don't know if you can hear my kitty in the background. The fourth term will be 5 times 4 minus 3, okay, and so on and so forth, okay? The 20th term, what's nice about sequences in this format is I can find any term without knowing the previous one. So I can just plug in 20 for n, which would give me 97 for the 20th term or the 20th number in the sequence. Okay, let's take a look here at the first 4. Do you notice any pattern here? Yeah, it looks like we're adding 5 each time, right? So you may remember from Algebra 2 that when you add a number each time, which by the way you could be subtracting because you can add a negative, that's called an arithmetic sequence, okay? So arithmetic sequence means you're adding the same number, and we call that the common difference, and we usually denote that with the letter D. So what was the common difference, D, for example 1? We said that was 5, right? So let's delve into arithmetic sequences and series a bit more. So in general, to find a term in an arithmetic sequence with a common difference D, then we're going to take the previous term plus D, right? So let's see if we can find a general formula here. So my first term is going to be a sub 1, we know that. My second term will be my previous term, so a sub 1 plus D, okay? My third term is going to be my second term plus D, right? However, what is our second term? Our second term was A1 plus D, right? So if I make that substitution, I get A1 plus D. In other words, my first term plus 2D. And let's pause there for a bit. Hopefully this makes sense, because if I want to find my third term, I would take my first term and add my common difference twice, right? Okay, so to find my fourth term, I would take my third term plus D, but again, I can make the substitution because my third term is that. So this becomes A1 plus 2D plus another D. So in other words, my first term plus 3D, because I need to take my first term and add D 3 times to get all the way to my fourth term, right? So can you generalize this for me? The nth term of an arithmetic sequence is given how? Like, how would I find my, let's say, 100th term? I would take my first term, then I would add D 99 times, right? If I want to find the 13th term, I would take my first term and add D 12 times. So in general, I'm going to take my first term, a sub 1, and add D n minus 1 times, right? So make sure you've got that written in your notes, please. All right, let's try some examples. Can you pause the screen and write what I have on the screen here, and then we'll work these together. All right, so the first example says, find a sub 10, so that's the 10th term, if a sub 1, in other words, the first term is 15, and my common difference is 4. So let's start just writing the formula again. So anytime I want to find the nth term, I would take my first term, and then I need to add D n minus 1 times, okay? So if I want to find the 10th term, I'm going to take the first term, which is 15. Now, how many times do I need to add D? Well, n minus 1. 10 minus 1 is 9. And D is 4. So we've got 15 plus 36. So what do we have here? 51. Okay, so the 10th term of this sequence is 51, and I got there without having to add 4 plus 4 plus 4 plus 4. We can get there a little bit faster with the formula. How about this one? Find a formula, just a general formula for a sub n. If the first term is negative 4 and the fifth term is 16. So my general formula, again, looks like this. So I want a formula for a sub n. Do we know our first term? Yes, that is negative 4. However, we don't yet know what D is, right? So let's come over here to the side and sort of think about that. Let's take my first term, negative 4. How many times do I need to add D to get to my fifth term, which is 16? I would need to add my common difference 4 times, right? If I start at negative 4, I would need to add my common difference 4 times to get to the 5th term, okay? So if I want to solve for D here, I get that my common difference is 5, all right? So I'm going to plug in 5 for D, and there is a formula. Maybe we want to simplify it a little bit. So if I distribute that 5, so here's a general formula for now any term in this sequence, okay? Notice that this, if you replace the n with an x, it should look kind of linear to you, okay? So instead of like y equals mx plus b, we now, your slope is your common difference, okay? So there is a lot of similarities between arithmetic sequences and linear functions, all right? Okay, so let's expand this a bit. Let's now talk about series. Well, what is a series? It is the sum of the terms in a sequence. So if your sequence is 2, 4, 6, 8, 10, your series could be 2 plus 4 plus 6 plus 8 plus 10, or 2 plus 4 plus 6 plus 8 plus 10 plus ... go on. It could go on forever. So just like sequences can be finite or infinite in length, series can as well, okay? And I would like to do a little bit of a review of sigma notation, okay? So we can condense a series using sigma notation. What does this mean? Well, this is what we call your index. So we're going to start with n equals 1, and then we're going to go through every integer between 1, and then we'll end at 3. So it's kind of your start and your stop. And where am I plugging these n's in for? Into that expression there, okay? All right, so if I plug in 1 for n into what I have in parentheses, I'd have 1 squared minus 1, right? Let's write that. Okay, then plus, I'm summing, this is the Greek letter sigma for sum. Now I'm going to plug in 2 for all my n's, so I would have 2 squared minus 1. Plus, now I'm going to plug in 3 for all my n's, so 3 squared minus 1. And I would stop there, because I'm stopping at 3. Okay, so I plugged in 1, 2, and 3 into n, and then we can just simplify. 1 squared minus 1 is 0, plus 3, plus 8. So I'm getting 11. Okay, so that's one way to condense sums. Okay, let's see if we can go the other way around. If I give you the expanded format, can you write this in sigma notation? All right, let's try these together. So I'm going to start with sigma because I can see it's a sum. I've got all these pluses. Let's look at each term. What does not change? Well, the numerator doesn't change, right? It's always a 5. Part of the denominator doesn't change. It's always a 1. But the other part of the denominator does. It looks like it's going 1, 2, 3, 4, all the way to 15. So use your favorite letter. N is used a lot for the index. And we want n, that moving piece, to start at 1 and end at 15. Is one way to write this. Okay? All right, let's take a look at the next one. We've got 1 minus 2 plus 3 minus 4 plus 5 minus 6 plus 7 ... plus 13. Okay? All right, so I'm going to start with this sum. Now, I can see it's going from 1, 2, 3, 4, 5. Let's use a different letter. Let's use K as another popular letter to use for the index. So K is running from 1 to 13, but there's a little bit of nuance here, right? Instead of 1 plus 2 plus 3 plus 4, it switches. And that's what we call an alternating series. It alternates between positive and negative. So when you've got this alternation, you want to play with the power of negative 1. Negative 1 to a power. Okay, so let's try this. If I plug in 1 for K, what do I have? I would have negative 1 to the 1 times 1, which would give me -1, right? Is that my first term? No, that doesn't quite work, but it's going to get me close. Let's make this k plus 1. Let's see if this works. So now let's plug in 1 for k. So I'd have -1 to the 1 plus 1, which is 2, times 1. Yeah, that works for the first term. Let's try the second term. Let's plug in 2 for k. Now I'll have -1 to the 3 times 2. -1 to the third is -1 times 2 is -2. And that works, okay? And so on and so forth. If we plug in 13 for k, the final term, we would get -1 to the 14th power, which would be +1, times 13. So that would work for us. So this is one way to express that sum. All right, let's try this last one. I've got 3 plus 7 plus 11 plus 15 plus 19. Does this look familiar at all? Or do you notice anything, maybe I should say? So do you notice that we are adding 4 each time? This is arithmetic, right? So maybe let's start with something like this. Let's start with 3 plus 4n, okay? If I plug in 1, what is that going to get me? That's going to get me 7, right? Which is actually my second term. So you could work with changing that expression. Or what about if instead of starting at n equals 1, why don't we start at n equals 0? Would that now give me my correct term? So if I start at n equals 0, my first term would be 3. That checks out. Then I plug in 1 to get my second term. That would give me 7. That checks out. Plug in 2 for n. That would give me 3 plus 8. That checks out. And so then the question is, where would I end? What would be my ending n value? In this case, if this is 0, this will be 1, 2, 3. I want to end at 4. Okay? So this is an important thing to point out with sigma notation. When your n starts at 1, it's usually very clear how many terms you have. Like the first sum I have up there, I had 15 terms. The second one, I had 13. What often happens is students will look at that last one and say, oh, I had 4 terms because the top number is 4. But be careful there. In order to get the total number of terms, we would take the top number minus the bottom number plus 1, right? Total number of terms, okay? Because top minus bottom just tells you how many terms in between. Then plus 1, you want to add that initial first term, okay? All right, so can we come up with some kind of shortcut for arithmetic series, just like we did for arithmetic sequences? Well, to do that, I like to go back in history a few hundred years to a very famous mathematician named Mr. Gauss. It said when Gauss, we think he was probably around like 7 or 8. He was a child prodigy, and we think that he was driving his teacher crazy one day and would not stop talking, and as punishment, the teacher said, Gauss, go over there to the corner and add 1 plus 2 plus 3 plus 4 plus 5 all the way to 100. And after a few seconds, Gauss comes and says the answer is 5,050. And the poor teacher starts adding 1 plus 2 plus 3 plus 4 all the way to 100, and Gauss was right, but Gauss did it much, much faster than his teacher. So here's the pattern Gauss figured out, and this turns out to work for any arithmetic series. So let's take a look at what we have here. Here's what Gauss did. Well, let me take 1 plus 100, the first term plus the last term. That's going to be 101. Now let's work in here. So the next would be 2 plus 99. Hey, that's going to be 101 as well. And 3 plus 98 is going to be 101. And as I work my way in, each of these pairs, when I add them together, will be 101. So really, all I need to figure out is how many 101s do I have? Well, I have 50 of them, half of 100, right? And that's how many pairs I have, and that's 5,050. Done and done. Okay, so let's generalize what Gauss did as like a 7-year-old a few hundred years ago. So Gauss, this is how we denote it, S sub 100, the sum of the first 100 terms. So how did he get the 101? Well, he took the first term plus the last term. That's how he got it first up here, right? And how did he get the 50? Well, how many pairs did he have? He did 100 divided by 2. Okay, so if I want to generalize this works for any arithmetic series. If I want to find the sum of the first n terms, I need to decide how many pairs I have. So I would take the total number divided by 2. And by the way, this works for an odd number of numbers as well. And then I want to take the first term, which remember we denote as a sub 1, plus the last term. So if there were like 100 terms, this would be a sub 100, or in our case, a sub n. This is our second very important formula for the day. Okay, so let's try some arithmetic series. How about this one? I've got 11 plus 7 plus 3 plus -1 plus ... and end at -73. Okay, so there are some numbers in between here that were not given. So I want to find the sum of how many terms? Well, we don't know yet, right? So let's figure that out first. Let's figure out what term is -73? Is it the 100th term? Is it the 13th term? Let's find out. So let's use our first formula for that. So a sub n is the first term. Remember this guy? All right, so I'm trying to find out what is n for -73. So I'm plugging in -73 for this last term. What is my first term? 11 plus n is what I'm trying to find. Do we know d? Yeah, it looks like d is -4, right? I'm adding -4 each time. All right, so let's solve for n. Let's figure out what term is -73. So I'm going to subtract 11 from both sides to give me -84. Let's divide both sides by -4 to give me +21 here. All right, so it looks like n is 22. What does that mean? That this is the 22nd term. Okay. Why does that help? Well, if I want to use Gauss's formula, I need to know how many terms am I adding up. So I'm going to write that in general. The nth sum is given by n divided by 2 times the first term plus the last term. I'm trying to find the sum of the first how many terms? The first 22 terms. So I'll have 22 divided by 2. That gives me how many pairs? And each pair is going to have the sum of the first term, 11, plus the last term, -73. Okay, so 22 divided by 2 is going to be 11. And then times -62, right? And then 11 times -62 is -682. And always check for the reasonableness of your answers. Is it reasonable that our sum is negative? Yeah, because look, we only have 3 positive terms in this series, and the rest would be negative. So looks good. Okay, how about something like this? Find the sum of the arithmetic sequence of series. So I is going from 1 to 10 of 6i minus 4. Is this arithmetic, first of all? Yeah, look, if you take this expression and replace I with an x, is that a linear function? Absolutely, okay? And remember, whatever your slope is, that's going to be your common difference. But if you're unsure, let's find the first few terms, shall we? So if I plug in 1 for I would get 6 times 1 minus 4, which is 2. If I plug in 2, I would get 12 minus 4, which is 8. If I plug in 3 for I would get 18 minus 4. Sorry, my kitty here. Okay, and so on and so forth. So you can see we are adding 6 each time. Let's do this also. What would be the last term? Well, I would plug in 10 for I, so 60 minus 4 would be 56, right? Okay, so I want to find the sum of the first how many terms? Remember, top minus bottom plus 1, so the first 10 terms. And again, the formula is n over 2, the number of pairs, times the first term plus the last term. Remember your 1 plus 100. So I've got 10 divided by 2. My first term was 2, plus my last term was 56. So I've got 5 times 58. So 290, yeah? All right. So just as a recap, for arithmetic sequences, our formula, I start at my first term and add d n minus 1 times. So again, if I want to find the 100th term, I'm going to add d 99 times after starting with the first. Arithmetic series, to find the sum of the first n terms, find your number of pairs, so n divided by 2, times your first term plus your last term, okay? All right, friends, check out that homework. Again, all homework for this week is due Friday at 9 p.m. And we will talk soon.